collisional origins. Before I talk about the inheritance, I will talk about the Wilson cycle, which is actually a way to explain how origins evolve through post-orogenic extension drift systems into oceans that eventually can be subducted and go back to origins. This process is well identified in the Pyrenees system, where it has been proposed that we start out with a Variscian system in the Carboniferous time that evolved through Mesozoic into extensional rift systems, leading to the opening of oceanic domains that have been closed during the Cenozoic and formed the present-day Pyrenees. Each of these steps creates an inheritance to the subsequent stage, but also some complexity, but which also creates some opportunities. If we think, for instance, about the Pyrenees, where we have the mantle rocks in Lourdes, we can explain how that the Permian mantle rocks have been exhumed to the seafloor in the Jurassic and Cretaceous, and then incorporated into the present-day Pyrenees. The possibility to trace rocks through a Wilson cycle, as well as to have this lateral evolution from the origin into the oceans, makes the Pyrenees to one of the best laboratories to study a Wilson cycle and the importance of inheritance from rifting to the formation of origins. But how important is the rule of inheritance, and how can it be studied? If you take a physical approach, you actually set up an experiment in which you define the initial conditions. You can measure the physical parameters throughout the evolution of your experiment, and you can define the final state of the deformation. This is not possible in orogenic or in geological systems, where you actually only find the final stage. However, in the Pyrenees, we have the advantage that we can find along strike the evolution from a rifted margin through reactivated rifts into an origin, which actually enables us to define the initial conditions, but also to understand the evolution from the initial state to the final state. In this presentation, I will address the following questions. The first question is how to define the initial condition inheritance in a geological system, how to link the initial state to the final stage, and what is the evolution of this system, and what are the physical parameters that control the system. The laboratory that I used is the Bay of Biscay Pyrenees system, which was our laboratory for the Origins project. In this talk, I will first look at the orogenic inheritance. That means the importance of the orogenic structure for the rift evolution, and then I will talk about the Mesozoic rift systems, and how that they defined and controlled the subsequent convergence. In part 1, I will talk about this orogenic inheritance and its control on rifting. If we talk about orogenic inheritance, we need to define first what we mean with orogenic inheritance. What you can find in this figure here is an equilibrated state of an origin at post-orogenic. That means after the post-orogenic extension. The crust is again 30 kilometers, but you can see that the former origin bears some inheritance, compositional inheritance due to the existence of suture zones, underplated material or depleted mantle rocks, but also some structural inheritance which is related to the grain that was forming during the formation of the previous orogeny. There might also be some thermal inheritance if the system is not yet completely thermally equilibrated. How important is this orogenic inheritance? If we go on the scale of the North Atlantic, we can see that for the Caledonites, the rift inheritance is important. The origin was split in two parts using rift structures. However, if we go into the Variscian, we can see that actually almost none of the rift systems penetrated into the Variscian. And if we are looking more carefully, we can see that the main rift the main Variscan structures have actually not been used by the subsequent rift events. Actually, most of the rift structures truncated or were oblique to the initially inherited orogenic structures, which actually shows or leads to the questions: why did the Variscan structures were not reactivated, at least not at the large scale, and how far the post-orogenic structures are important in setting up or even in taking away the main structure of the Variscan. The main results from the Origin project related to orogenic inheritance were the study of the nature of basement and basement structures and their control on the subsequent rifting. We also investigated the so-called granulite paradigm, and we implemented the Variscan domain structures in a new plate kinematic framework. There are nevertheless some remaining questions, such as what is really the Variscan paleogeography and how can it be restored? How far did the post-Variscan collapse overprint the Variscan structures and modify the cross-lithospheric composition and erase Variscan inheritance? And how important are the Variscan and late post-Variscan structures during rifting? In the second part, I will talk about the Mesozoic rifting in the Biscay-Pyrenees domain, and I will mainly address the question about multi-stage versus polyphase rifting. If we go into the southern North Atlantic, we can actually see that rifting was the result of a multi-stage multi-phase rift system with three main phases. The first phase was a Triassic distributed extension that can be found throughout the area, often related to salt. A second event is related to the localization of rifting, and in the Pyrenees to the evolution of a strike-slip movement of Iberia relative to Europe that is overprinted in the Cretaceous by orthogonal hyperextended evolution. There is a strong link between the kinematic framework in the southern North Atlantic and the link and the relation of the Iberia-European plate boundary. Also, the initial stages are not so well understood. We believe that transtension is an important process during the late Jurassic, which is afterwards overprinted by hyperextended basins that are shown within these green domains. In the Origin project, there were 4 PhDs, 2 postdocs, and many researchers of the BRGM that studied the rift evolution and the importance of rifting for the subsequent orogenic event. These studies they led to very interesting results that can be found on the homepage of the Origin project. Most of the projects were focused on the area between the Bay of Biscay and the Pyrenees system, and in this study I will mainly focus on the area between the Bay of Biscay and the Pyrenees, because this is the place where we can go from an inherited rift template across an area that was overprinted to an orogenic system. I will focus to some of the results, but cannot show all the results that resulted from the Origin project. In the west, in the Sturia Basin, we were able to find a very important depot center that is well imaged in this dip line. You can see that you have up to 4 kilometers of Upper Jurassic, Lower Cretaceous sediments that have been drilled and that are confined within a fold-bounded losange type basin that is probably a pull-apart basin. In strike sections, you can find that these basins overprint earlier Jurassic basins. And if we go further to the west, we can find on this section that we have preserved Triassic basins related to salt tectonics that are sealed by the Jurassic here in blue, and overprinted by later Cretaceous extensional detachment systems. So the major observation is that we can find 3 events of extension that are not related to the same kinematics and do not accommodate the same way extension. If we go in further to the north and look more carefully to this Cretaceous event, we can see that we have a top basement that is structured with small extensional allochthons. We can also find that there is some reflections that come up towards top basement, and in the top basement out here, the line drawing, we can find granulites that have been dredged at the seafloor. And this leads to the interpretation that crustal thinning occurred along low-angle detachment faults that exhumed upper middle crust that were from where the granulites come from. These were sealed by Cretaceous sediments that are soon tectonic to the detachment faults, indicating that exhumation of granulites and crustal thinning occurred during the Albian hyperextension. So the main learnings that we got from the Pyrenean rift system is that we can subdivide the extensional evolution in 3 events. Triassic low beta stretching stage, where we have also salt deposition. We have a transtensional pull-apart basins that are Upper Jurassic, Lower Cretaceous, and a high beta, hyperextended late Aptian to Cenomanian event that is structuring and forming the major rift basins. We did not find evidence for polyphase rifting, but we have more a multi-stage rift evolution where the different rift events overprint each other. In some places they are separated, like for instance in the Asturias, whereas in other places these systems are overprinting each other, which leads actually to seek pre-rift Jurassic sequences in very distal parts of the hyperextended domains. A very interesting situation that I will discuss later on. So the major results by the Origin project were the identification and mapping of multi-stage rifting, linking rift evolution with the plate kinematic framework in the North Atlantic, and the definition of the rift template, including segmentation and fold arrays. There are some remaining questions that are related to the rifting, like what really controls the rift system? Is it inheritance, the stress field, or the plate kinematic framework? What is the importance of the Triassic rifting and related salt? And what is the polarity of the main thinning faults? In the third part, I will now talk about the role of rift inheritance in controlling the reactivation. In this slide here, I will show 3 sections through the Basque, Cantabrian, and Pyrenean system. The western section is in the west in the Asturias. The central section goes through the Basque Cantabrian system, and the eastern section is across the Basque Mollon system. You can see the restoration in the Campanian and during the end of major extension in the late Albian. In the following, I will compare the western to the central section first, and then I will go to the east and look at the overprint of a segmented fold array. If we compare the western and the central section, we can see that these sections are very different. In the central section, we can see that Jurassic and Triassic rifting was directly overprinted by the Cretaceous extensional event, and that during convergence, the serpentinized mantle was probably playing a very important role before salt became the main decoupling level, and the infill is completely decoupled from the deformation in the basement. In contrast, in the western section, we can see that the Triassic and Jurassic extensional event was actually not occurring the same place like the Cretaceous event. There is not a lot of salt actually in the distal parts of the Asturias basin, and of the Stura margin, and shortening occurred in the north first by reactivating serpentinized décollements before it shifted back into the continent and reactivated some of the rift structures. But most importantly, the formation was more coupled and salt was not as important. If we go to the east, and if we are looking at the segmented rift system between the Basque-Cantabrian and the Molion Basin, we can see this evolution in here in 3D, looking towards the west. This is the Basque-Cantabrian Basin, this is the Molion Basin, and this is the reactivation through time. In section A, we have a restored section through the Basque-Cantabrian and the Saint-Jean-de-Luz Basin, which is the termination of the Molion Basin. And we have in between the block, which is made up by the Basque Massif. During reactivation, the formation initiates in the hyperextended domain, and the Basque block is somewhere in between as a keystone. Whereas further to the east, the section through the Molion Basin shows complete reactivation of this basin. If we're looking this in a sequential sections that are from west to east, through the initial rift event to the present day situation, we can actually see that the hyperextended Basque-Cantabrian Basin, this is section A, and Molion Basin behaved very similar. The basin was completely inverted, mantle was subducted, and there is a decoupling between the infill and the crustal structures. Whereas if we go to the section B, which is actually in the array zone in between the two segments, we can see that the Basque Massif is actually surrounded by the domains that are extending, and we preserve the rift structures that are being surrounded by the extended systems. The most interesting section is, however, that section C. In the section C, we can find that there is a shortcut during convergence, which makes that the thrust is actually cutting into the mantle, and some part of the mantle is in the hanging wall of the thrust, which actually makes that you cannot subduct it anymore, and you keep it in the crustal structure between this blue fold, which is the northern Molion detachment, which is related to the exhumation of the mantle, and the later thrust. If we are taking these sections and compare it to the position of the high velocity body, which is also a high density body in the Molion Basin, we can see that the section C, where we have the mantle within the origin, is actually exactly over the area where we have the anomaly. Whereas if we go to the east or to the west, we do not have this anomaly anymore, because in the east the detachment is the mantle is being subducted, whereas in the west we have a continental block in this position. This fits also very well with the Montperzac, with the results of the Montperzac experiment, where you can actually see that this high velocity body is exactly in the same position like in this model by Lescoutre. And this is despite the fact that this model has been set up before these results came out. So it's a very nice result of the Origin project, that the study and the mapping of rift structures and their inversion can explain very well the results of the Montperzac experiment. So what we learned by looking at the inversion of the North Siberian rift system are three parts. The first part is the rule of décollement levels. We can see that during the rift evolution, we set up three potential décollement levels, which are in the hyperextended and exhumed mantle, the serpentinized mantle. In the necking zones, the middle crustal levels, and in the proximal parts, salt. Salt can also occur in the other parts if there was an overprint between the Jurassic and the Cretaceous rift events. The most important thing is that these decoupling levels can be sequentially reactivated. You first initiate it with the mantle décollements before you go into the middle crust and finally end up with salt. If salt is present everywhere, salt is the most important décollement level. But most importantly, each rift domain evolves in a different way and is reactivated in a particular way. The second learning is about the lateral and the long strike evolution related to rift inheritance. What we can see is that convergence initiates and in each of the segments before it makes shortcuts, and eventually it leads to a reorganization at the moment of collision. This can explain that in the western section the subduction fails and the formation is actually stepping back into the continent. If we are summarizing, we can see that rift inheritance is very important, in particular for mature rift systems, which actually control, in particular, the early stages of convergence. In contrast, the final stages of convergence are probably more controlled by the more Coulomb theory and are less dependent on rift inheritance. Are there other controlling factors that we need to take into account that are related to rifting? Yes, of course. There are the thermal structure and the salt. The BRGM did a very good work in analyzing the thermal structure of the Molion Basin, and Nicolas Saspuri actually showed the importance of the thermal structure during convergence. It's interesting, however, to see that if you go further to the west, to the Bay of Biscay domain, that actually the localization did not start at the mid-ocean ridge. That can be supposed to be the area with the highest thermal gradient, but it occurred into the margins, which actually leads to the question if the thermal structure is more important than compositional weaknesses related to rift-inherited décollements. More about the thermal structure will be presented by Maxime Ducou in the following presentation. What is the importance of salt during rifting and convergence? If we are looking at the western and the central section in the Asturias and in the Basque-Cantabrian systems, we can see quite a difference. While in the east, in the Basque-Cantabrian section, salt is everywhere and seems to be very important in decoupling between the infill and the basement. In the western section, salt is actually not very common in the distal parts and occurs only on the proximal parts and in the necking zone. So this can be explained by either the fact that salt was as important in the western part comparing to the eastern part of the Pyrenean domain, or by the fact that in the west the Jurassic and Triassic rift systems were not occurring in the same place like the Cretaceous, whereas in the Basque-Cantabrian basin, these rift events were overprinting each other, which actually leads to thick Jurassic and salt sequences in the hyperextended domains. More about the importance of salt, and in particular also the importance of salt in the Eastern Pyrenees, will be presented in the presentation of Marie Ford. To conclude and to give an outlook, I will basically go back to the final question, which is probably also the question that we had at the very beginning of the project of origin, namely, can the Basque-Cantabrian Biscay-Pyrenean system serve as a global model to define the rule of rift inheritance in building collisional origins? Before I try to answer this question, I would just like to go back to one point which is very important. The Origin project was not only about trying to understand orogenic systems in the Pyrenees. It was also in trying to define inheritance and to try to use it to implement it in conceptual analog or dynamic models. From our understanding of the study area, we can now say that the conditions at onset of multistage rifting were thermally equilibrated. And we can also say that it's surprising that the Vriskin orogenic structures seems to play did not have a very strong control on the rift evolution, at least not on a large scale. The conditions during hyperextension seems to be mainly controlled by the multi-stage rift evolution, in particular by the transtensional evolution and the occurrence of salt during the latest orthogonal hyperextension phase. The heterogeneous heat flow is actually difficult to understand in detail, but it does not seem to have led to strong crustal flow and to the occurrence of magmatic events during hyperextension. Salt is very important, in particular in the necking and the stretching phases, but locally it also occurs in the hyperextended domain. The state during the end of hyperextension and the onset of convergence seems to be controlled by a very high thermal gradients that are localized to areas where there is a lot of sediments, some late to post-magmatic events, and very important is also the occurrence of fluids. The crustal structure is defined by a very strong anisotropy, by pre-structured décollements, and is very segmented. It's by far not a layer cake, and the juxtaposition of strong and weak layers is very important in defining the places where shortening occurs first. And finally, the material parameters seems to be very strongly controlled by the maturity of rift systems. So to finish, I would like to go back to the question, can the Basque Pyrenean system serve as a global model to define the rule of rift inheritance in building origins? Before we talk about building origins, we should actually go back and think about how far can the Basque-Cantabrian system and the Bay of Biscay be compared to present-day oceans. We can certainly say that the Bay of Biscay is certainly not a magma-rich system. It's much more a magma-poor system. And if we go into the Pyrenees, we can actually demonstrate that there was no ocean there. The new tomography images clearly shows that no ocean occurred in the Pyrenees. So that means that we do not deal with a white ocean where we have subduction-induced processes such as back arc basin. We probably never had a slab pull forces. We are probably more related to narrow oceans or even intercontinental rift systems where you need external forces to drive the orogenic evolution. So the orogen in the Pyrenees is certainly not one of the big ones that was post-dating the subduction of thousands of kilometers of oceanic crust, as you can find further into the east in the Himalayan type orogens. Nevertheless, it's very important to realize that if you go to many of the orogens, like in the Apennines, in the Alps, Zagros, Oman, or Taiwan, you can actually see that you can find a very similar evolution and a stepping from inboard to outboard using different rift-related décollements and décollements, initiating with the reactivation of exhumed mantle, stepping into the necking zones using intercrustal extension, and where present also salt. So that means actually that the Pyrenees allows us to learn a lot to understand other origins. It's probably mainly when you have the subducting lower plate, when it comes into collision, that it might behave very similar to what we can find in present day in the Biscay-Pyrenees system. These are results that actually might show that we have some global learnings in the Origin project, but these are also things that we need to further explore in a more global way. I would like to acknowledge the partners that supported the Origin project, like Total, BRGM and INSU. And I would also like to thank the whole Origins team.